Okay, so Unit 4, Part 1, we're getting into industrial materials, and the very first one is ferrous alloys. We use alloys because it's less expensive than the pure ones, and ferrous alloys, they're the largest portion, okay, of our industrial materials that we use today. And also they're totally economical, and then they're available. So we use in construction, heavy machinery, and also parts, that need load-bearing capacities. And we'll get into that in the chapter all about it. So in ferrous alloy, we will get into steels. We all know what steel is, and then cast irons, because each of them, they offer uh, properties to meet our industrial needs. Properties like mechanical strength, ductility, corrosion resistance, and wear resistance. So if you think about steel and cast iron, you can change them, okay, by using alloying elements, and also by heat treatment. Heat treatment is nothing but we just heat it up, okay, and you will see different kinds of properties arise from the end materials. We'll also look into the composition, structure, and properties altogether in ferrous alloys. So let's go to the next slide. So if you think about ferrous alloy, they're just iron-based alloys, okay? Because from ancient time, the very first two, um, metals that we started to use in mass production is iron and steel, right? So iron-based alloys are, we call them ferrous alloys. Nobody used this name outside, okay? We always say like, we don't even say like iron-based alloys. We only say iron alloys, or steel, okay? So 80% of metals used in the United States, okay, for industrial applications, they're completely iron-based. So iron and steel, they're popular because first thing is they're cheap, okay, low cost. They have high modulus of elasticity, meaning they can break easily, okay? And iron is actually more breakable than steel, but then we can manage it. We can control iron, so we can increase this modulus of elasticity in there, okay? And they also possess wide range of attainable mechanical properties. Attainable meaning like we can make it, okay, make it happen. Yes, so when we get into the composition, ferrous alloy, even if we say ferrous, Fe for iron, when we add the alloying element, we usually add carbon, because it's easy, okay, for carbon to get into iron. So ferrous alloy is nothing but you have your iron and you have certain percentage of carbon in it, okay, and we call those kind of mixed metals metal with something else alloy, okay. You can also add silicon and manganese, right? Because if you add silicon and manganese into iron with carbon or without it, it's going to improve the mechanical properties. On the other hand, when you think about sulfur, and phosphorus, they're impurities. So if they get into iron, it's detrimental to iron mechanical properties. Okay, so we don't want this too. And steel is our industrial material. We use it all the time, and it has less than 1.7% carbon. Cast iron, we have 2 to 4% of carbon. So only the composition of carbon is changing. Look at the percentage. So if you have like 1.7 carbon, you've got steel. If you have like 2 to 4%, alright, carbon, then you've got your cast iron. This is what steel look like outside, and then there's cast iron look outside. See, not so much percentage of carbon. So this is what I want you to understand about how powerful it is for these elements, okay, to mix with another element, and they can change the outer appearance, alright, drastically. So the quality can change drastically. So inside, the atomic structure level is not so much, see? But outside you can see drastic changes in appearance, yeah? Okay, so we get iron from iron ore. So what we do, we're going to change the iron ore into something called the first raw material, and we call that pig iron. So pig iron, it has like about 4% carbon, right? 4%. So pay attention to the percentages. So that's what I will be asking you in midterm. So even though it is like an open book, you still have to know, right, where the materials are to answer the question. Okay. So iron ore, we usually mine it out from the ground, okay? And what you get is like iron oxide. So that's our iron ore raw material, Fe2O3, okay? So like I said here before, we're gonna convert iron ore to pig iron. And what do we use? We use a blast furnace. You need heat, okay, to change appearance or structure. So this is a chemical reaction that happens in the furnace. So you have your iron ore raw material, and we're going to blast it, okay, in the furnace. So that's carbon monoxide, usually come from your flame. They all mix up, and you got iron. It's pretty molten like that, okay? Because of very, very high heat, iron, it melts into molten iron or liquid iron. Carbon monoxide, it's going to go out in the way of carbon dioxide, okay? And this is very obnoxious for you. If you breathe so long, you die. So that carbon, right, here is your molten iron. It's so hot, okay, very, very high temperature. So what happens is this molten iron is going to trap the carbon, okay? The carbon is going to pass through coke at the bottom of your furnace. So, but you don't have to remember all the process. All you have to know is we have Fe2O3, that's your iron oxide, and we're gonna flame it so high, okay? to very, very high temperature, iron is going to melt into liquid. Since they're burning, we always have carbon monoxide and carbon dioxide. And from there, we're going to get the carbon. Alright, and that carbon is going to be absorbed by this liquid iron or molten iron. Yeah? So that's how iron will go into the iron. So you'll be getting pig. This is pig iron right after the ore flame, okay? And you can make steel out of it. So this is where the iron ore iron is going to be converted into pig iron. So where we're heating, and it's very, very, very hot inside, okay? They're running like 24 hours a day, 7 days a week, because they have to make incredible amount of industrial products right in there, right? So construction people will say, oh, I need material, I need material. So we cannot imagine if something happened here, right, in this factory, right? The loss is going to be really big. So if you look from outside, if you drive by a factory like this, and you think like what, looks weird or something, but this is a money pit right in there, yeah? So most of the steel we're using today, it has like less than 1% carbon, because pig iron, it has excess carbon, and that excess carbon got to be removed before it can be converted into steel. So in other words, your pig iron has more carbon percentage than your steel. Okay? Don't forget that. So if you take a look at the technique, we just use a basic oxygen furnace. So usually, if you don't know what that is, it's very simple. You have a closed bottom, and you have a refractory line vessel. Vessel is just a big container. So we're going to add the molten pig iron, that's just a liquid iron. And then we're going to add your recycle or ST scrap. We always get these scrap from like welding lab, right? You can see all the scrap come on, go and throw it out in the recycle center, and somebody's going to pick everything up and back to the factory, okay, manufacturing factory. And you add a little bit of lime, and then you add fluorspar into the furnace. So this lime and your fluorspar is going to create something called slag. And we're going to add a very, very high velocity, meaning like it's a very high speed, and steam, really hot. So steam or oxygen directly down the molten mixture. Okay, so oxygen itself is not hot, but you're dealing with a liquid molten, liquid iron. So when you exerted a steam of oxygen, that's burning hot because oxygen favors the fire. Yeah. When you put it down directly to the molten mixture and through, and you have to use a cooling agent, and we call that the water-cooled lamps. Okay. And that causes a very rapid oxidation of carbon. Oxidation of carbon meaning like we're taking the carbon content out of it, okay? Because now carbon is going to be with oxygen, so the carbon is not going to be in the pig iron. So we will be reducing the carbon content. 4% in pig iron molten, and we're going to bring it all the way down to 1% in steel. Yeah. How do we get rid of carbon? We're going to let it oxidize. Yeah, that's what I'm putting. Look at this, oxygen into it. So carbon and oxygen, they form a carbon dioxide or some sort of oxide, okay? So you can get rid of about 3% carbon from your pig iron. So we're going to add the deoxidizer. And we're going to add some alloying elements from your periodic table, right? So that's a lot of research right in there. You add this, you add that, and then you record it, what happened, you record it, and everything that is going to increase the machinability or strength or ductility, okay? Everything that we desire for construction, then we remember which alloy we added and we continue to use. So that's how everything started. So here we add the oxidizer. Then we're going to add the alloying elements. And then we're going to remove the steel from the furnace. Yeah, that's just like polishing. So here, that's how steel look like. So again, when the steel come out from the furnace, it's like a liquid. You have to make it into shape. Yeah. So we're going to pour it into the ingot molds. Okay, ingot molds, or continuous casting line. And we call that the steel rods. So the steel rods, we're going to fabricate it, okay, into two shapes. Now we start to use our mill. So we have piercing mill, we have reducing mill, we have elongator, and we have a rotary sizer. So we're going to shape, right, the steel rods. And fabrication process starts here. And then put all the tubes on thermal and mechanical treatments up to the properties we want them to have, okay? Then we're going to ship and distribute it. If I ask you this, you should be able to come up with it. You can write it step by step like this, or you can also draw equations, okay? Whichever way you want to do it. I write it down for you because if I write the equation, some of the students can follow because they haven't done chemistry or something, so I just put it in English for you, yeah? My preferred way is I usually write like in the equation form, which is, for my brain, I like equations more than reading, a lot of sentences like this. My brain can't catch this. I usually draw, okay, or write equations. So that's up to you. So here I recognize American students their strength is in reading, and so whatever you want to do. Okay, all I want is I want these steps. When I ask you how to make steel, you gotta tell me, okay? Okay, this is just a diagram. I'm just showing you this high-speed steam, your oxygen flow, okay, into the molten iron. So here you can see this little water-cooled hood right there. Then we have this oxygen lenses here. And then at the bottom, okay, this is your refractory lining. Okay, and that's just your steel shell. So the reaction is right inside. We're just doing oxidation of your carbon because we want to remove the carbon about 3% from pig iron. Okay, so we get steel with 1% carbon. So this is just from your handout, okay, and you can take a look at it and make a bigger picture. So just showing you from melt to finish. Right here, little shipping truck right there, okay. And here we're melting and using the furnace, so you can take a look at it, that process, okay. I'm not going to iterate it. Alright, now get into cast iron and what cast iron So this is your cast iron, and that one is your white cast iron. You can never remember how they look like because they all look the same anyway. We remember by reading, okay, there's a tag, there's imprints right in there, so you can just go and see what you have, okay. They all come probably like at the one end, and you can read, right, the codes right in there, so you know what material you're dealing with. So cast iron, we're going to convert it again from our pig iron. Pig iron is converted from your iron ore, right? So now we're going to make cast iron from pig iron. So we use a smelting furnace. We also use the electric induction furnaces because it's faster. So first you add your pig iron, and you add your recycled scrap, okay? And then you add your scrap steel. You add a little bit of your limestone to the furnace. Heat it up to a very, very high temperature. And then we're going to add alloying elements, okay, to form a special structure, yeah, inside. And you can see different properties outside. We're going to add that into the molten metal, which is your molten iron. Then remove it from the furnace and then cast. That's just making shape, okay, in the way you want. Usually sheets or strips or rods, because they're basic industrial material, and from there we make some more, yeah. So for cast iron, it has higher carbon content than steel. So the carbon in cast iron is usually in the form of graphite, okay. So when you think about carbon, they come in different forms. You have pure carbon, you have diamond carbon, you have graphite, okay, and you have your ash carbon, right? So that's just chemistry. I'm just gonna give you a little bit of review for you, so you kind of get it. They stay in gas with oxygen, right? So it also has higher concentration of silicon, right? I'm gonna put a little bit of limestone, okay? That's another one is we're gonna put higher concentration silicon. Then we're gonna put carbon, which is higher percent than the carbon in the steel, okay? And that carbon is going to be in the form of graphite. So the high carbon and silicon concentration make cast iron hard to deform. So if you think about cast iron, I believe you will definitely think about your cast iron pan right in your kitchen, because that's what you use all the time every day. If you have one, and it's pretty hard, right? You can completely lift it up, and it's very heavy. It's also difficult to deform, and that's because you have really high carbon percentage and you have really high silicon in it, okay? So special purpose cast iron, it has elements, okay, other than silicon and carbon. We have like manganese and nickel. We also add chromium, copper. So why do we add these things? Because we want to know what happened, okay, if we add them to cast iron. So what do we get? We get special purposes, meaning like they come with properties, okay, different properties, like improved corrosive, okay, resistance or abrasive resistance or high temperature application, okay, they're capable of that. So these are all special cast iron because we're adding alright, element other than silicon. Okay, silicon make cast iron real hard. These elements, okay, make cast iron to be like corrosive resistant, abrasive resistance, and also withstand high temperature, okay, applications. Another cast iron is called white cast iron. So it contains carbon, but again in the form of iron carbide or cementite. Cementite is nothing but it's just the iron carbide. We call it iron 3, alright, carbide, Fe3C. So let's wrap it up before you get confused. White cast iron. The carbon is in the form of carbide. Cementite is nothing but it's just iron carbide. Okay, in details, is iron 3 carbide. We have special purpose cast iron. That's because we have different alloy elements: manganese, nickel, chromium, copper. What happened to the cast iron? They become more corrosive resistant, abrasive resistant, and they can stand high temperature applications. Regular cast iron, it's got carbon, alright? That carbon content compared to steel, alright, carbon content is higher, yeah? And it's got silicon, very, very high concentration, okay, in it. Okay, now this is how we make it process, pretty simple. Then we're gonna get into plain carbon steel, alloy steel, and high alloy steel, okay? They're kind of different. Again, you can't differentiate because they all look alike. How do we differentiate? We read, okay? We read the engrave on, or sometimes they have tag, okay? Usually it's printed in the product. So plain carbon steel, they are just alloys. And PCS, it has just iron and then carbon, okay? And it doesn't have a significant amount of other alloying elements, okay? Mostly iron and carbon. So we call it plain carbon steel. Alloy steel is we're gonna add alloying elements less than 5% in total, right? Add that, and we call alloy steel. So what's in it? It depends on what alloy that is. Okay. High alloy steel, you have large amount of alloying elements. Okay, definitely more than 5%. Okay. So why are we adding different alloying elements? Because we want different quality. Okay, we want it stronger. We want it better. We wanted more tensile strength. Okay, we wanted more corrosive resistant. We wanted more abrasive resistant. We want them to stand on very, very elevated temperature. Okay, so we have to try with different alloying elements. Okay, different percentage. Okay, so iron 3 carbide phase diagram, iron and steel properties. Alright, we're going to go back down all the way to our microstructure again. I told you so many times, in order for us to control the properties at our level, we have to control at their level, which is your atomic structure or microstructure. So in order for us to control the microstructure, we have to understand the phase diagram. So we have iron 3 carbide. Pure iron, already told you, is a body-centered qubit. Body-centered qubit. So here you can see the entire body inside, okay? Look at that little, right? Inside, okay? So body-centered qubit, and that's a pure iron microstructure at room temperature. And we call iron with this type of microstructure alpha iron. We're going to heat the alpha iron to 1674 degrees Fahrenheit. Okay, that's very high. So this thing is going to transform to that thing, which is another microstructure. So it's kind of like you're changing, all right, the way they're attracting each other. So now look at that. So you have face center qubit, and you have a gamma ion. So this structure, you have to heat this up, BCC. So you get FCC, which is your face center. Face center, look at that. See, you don't have anything inside. Okay, everything is chopped up. Here I have a one whole, right, atom right in there. So here I have all the chopped up. This is not inside. This is on the surface. Okay, so you can see this block is actually this one, and that one is actually this, and this one is actually that. Okay. So I always remember there's a one whole atom right in here, and there isn't in face center because all the phases are on the surface. Okay. So we're going to heat this up, FCC, to 2541 degrees Fahrenheit. And it's going to transform to BCC into a delta ion. Okay. So what's the deal? The deal is your heat. Every time you change the heat, you can see the microstructure changing. First change from here to there, and then change from here back to here. See how they're switching the form. And so in physics and chemistry, we study in this kind of switching form. That's the best they can do, okay, in the space that they have switching back and forth. See, so here 1674, and here is a 2541. So when you take a look at it, the temperature difference is, all you have to do is subtract it. Okay, I'm going to subtract it for you. So 1674. So you got like 867 degree difference. Yeah. All right. Anyway, you get it. Very simple process. The most important thing is we are heated up. Very elevated temperature. They change their microstructure. Okay. And how are they linked to what industrial material our interest is? Because they're linked to the properties of iron and steel. Okay. So what's happened inside at the very, very, very atomic level is what kind of properties we're going to get at our level. Yeah. You don't have to know this in details at all. This is just showing you the iron-iron carbide phase diagram. It's just showing you the various possible phases present. Okay, various possible phases present in iron and steel at different compositions and different temperature. So what do you have to know out of this little picture? Change in temperature, change in structure. That's it. Yeah. We call that the phase. Phase meaning, like, see that you have your gamma here, and you have your delta here, gamma here again. I can find here. There's your alpha there. Okay, and here is my alpha. Okay. All right. No need to remember any of this again. Try to pay attention to all of the phases, which is your microstructure, right here. And there's alpha a little bit here. Your gamma here. Okay. And remember the changes in the temperature. Yeah. Ferrite. Okay, so we got into iron, different irons. So first one is your ferrite, and that's your alpha. We call it alpha iron, commonly outside. Okay, that's just a chemical name. People don't use this outside, so just go with the alpha iron. So if you say offer iron, you know we're talking about a ferrite. So here what it looks like outside. Okay, so at very low temperature, you're going to add a small amount of carbon. Okay, you already know how to get your the pig iron. Okay, so pure iron, we're adding different percentage of carbon. So here we're going to put a very little, right, amount of carbon into the pure iron or offer iron. So carbon atom, they're going to distribute right in between the iron atoms. So we go back there, we have like an iron atom right there, an iron atom. This is just exaggerated, okay? And then you might have like a carbon atom, okay? And the iron is bigger than carbon in the periodic table, so don't forget that. So the point is, they're going to distribute between the iron atoms. And we call the structure of a ferrite. So if you increase the temperature, alright, we can spike the carbon into the iron even more. Yeah. So make sure you control the temperature for the amount that you want, right? In the iron. So if you want a little carbon amount, you don't want to heat it up so high. So when you take a look at it, 32 degrees Fahrenheit, you have 0.005%, and 1341, you have 0.022%. Quality, very soft and easily deformed. Why? Because we have very small amount of carbon in offer iron. Okay? I'm going to erase this for you. Okay. Austenite. Okay. Austenite. I want to go back to this. Okay, I got it. Austenite, we call it a gamma ion. So here you can see that's the austenite, and see the little boundary here. So we're going to heat it up, okay? So when you heat it up, the carbon is going into the iron, yeah? So how much percentage we want it to be in? 2.08%. And at that time, the structure is like this, and we're going to call it austenite, okay? So if you think about the ferrite, offer iron, when you compare it, we know that based on this 2.08%, so austenite, it has more carbon in it, okay? So at what temperature we're dissolving the carbon into the iron is 2098 degrees Fahrenheit. Quality, it is ductile, you can draw, and easy to deform, okay? Draw means there's elasticity, yeah? Cementite. So cementite is an iron-carbon compound, and we call it Fe3C, iron 3 carbide. Okay, a chemical name. We have 93.3% iron, and we've got like 6.67% carbon. Can you see the carbon percentage going up? And we call that cementite, right? Pig iron has like 4%, steel is 1%, cementite, it's got like 6.67. 2% is going to be in austenite, okay? So quality, cementite is hard, breakable, brittle, yeah? This is how we heat things up in a furnace. Okay, going into steel. So steel, we're going to reduce the carbon. So averages, we call it 1%. so 1.7% carbon, and we're going to put other alloy elements, and then we have our base iron. Okay, so 3 different types: plain carbon steel, alloy steel, and high alloy steel. This is just from the previous slide to compare, and I've already told you about that. So 0.5% carbon, and that is austenite. That's at 2000 degree Fahrenheit. For ferrite and cementite is at 800 degree Fahrenheit. Okay. So you might say, oh, what's the difference? Okay, you have the same amount of carbon. Oh yes, but this is kind of like cooling it down, alright, from this temperature to here with the same amount of carbon, and you can see the phase changes. Yeah. So austenite is gonna go back to your offer and then to your cementite. Okay. Alright. So for steel, the higher the carbon content, this guy right here, the quality is gonna be harder and stronger. Right. Tensile strength goes up. So we now know carbon, okay, is a guide, yeah, because it can significantly affect the crystal structure and also the tensile strength. Tensile strength is nothing but we call it the mechanical power, yeah, tensile strength of this industrial material, your steel, okay. Well, you have to get iron and steel, right? So please study. Plain carbon steel, PCS. So when you look at it, we have 1.5% carbon, and that's the maximum it can go. And I said it again, maximum it can go. And we put a different alloy elements, right? Just a small percentage. So you can put like maximum 1.6% manganese. You can put like maximum 0.6% silicon, maximum 0.6% copper. And you can put like maximum 0.05% sulfur. And you can put phosphorus, right? 0.05. You know now how to make steel, okay? We already told you it's all about the material and the heat, yeah? And what you're putting into it, mostly carbon and some alloy elements, okay? That's all we can use, by the way. Okay, now let's introduce you AISI, okay? This is just American Steel Institute code 1040. They have code like that. It's just telling you the plain carbon steel with a nominal carbon content of 0.40%. So we call these, like when you're doing like purchasing or something, we go with a code and we call that steel code. Nobody say AISI number, right? Outside, everybody says steel code, and this is it, yeah? So AISI is again your American iron and then steel and then institution, okay, institute. So this table is just showing you the composition. So you can see the percent carbon and one of the alloy element, percent manganese. Okay, that's what you can be able to put into it. And here is the maximum. You cannot go more than that. Okay, it's going to mess up the properties. So here is your phosphorus and your sulfur. You can put max 0.05. You can put phosphorus 0.040 max. Okay. You got the idea. No need to remember any of that. Okay. But if I ask you 1035 and I'm going to give you this table, you know, okay, how many percent of carbon is in there and how many percent of manganese in there. And don't forget, you have this other two as well, yeah? Okay, next table. Another one here. So this table is just showing you applications of PCS. So your typical applications, okay? I have my mild steel, I have a medium carbon steel, and I have a pretty high carbon steel. These are just differences is like the percentage of carbon, yeah? So you can see 0.2%, 0.25 to 0.65%, 0.60 to 1% carbon, okay? And property, when you look at it, construction, we use it because that's pretty inexpensive, cheapest, yeah? You can machine it, you can weld it. Medium, we use in automotive, okay, parts. You can heat treat. Then your high carbon, we use it for cutting tools. And it's pretty expensive because it's very durable, yeah? And here you can read. I don't want to read all of that for you. Yeah, this is just showing you where we use the stuff. So here for high carbon, because it's very durable, we use in wood cutting tools, the razors, the drills, the milling cutters, so on and so on, yeah? Alloy steel. So alloy steel is steel with added alloying elements. So we add them to make steel better and more useful. So why do we have to do that? We want to improve mechanical properties. Mechanical meaning like we're making it stronger. Resistance to corrosion, okay, resistance to high temperature, resistant to oxidation. So what are we improving? We're making it stay in use longer. Special properties. We're making steel resistant to stress, fatigue, and abrasion, okay? To be like abrasive, like resistant. Then we want to improve hardenability. So what are we doing in here? We're making the steel more heat treatable, okay? So you can shape in many different shapes you want to manufacture. Okay, next table. No need to remember any of it. This is just showing you the classification for standard alloy, okay, steels. So here composition in percent. So here's the type, and we have these, okay, alloy elements. Manganese 1.75%, molybdenum we can put that to 0.2% to 0.25, okay. You can also add sulfur, anyway, chromium, nickel, blah blah blah, chromium, silicon, okay. Alright, so by looking at this table, you should be able to know alloy elements, okay, that you can put into the iron to make steel. So these are everything, yeah. So I'm going to give you some choices. So make sure you get all of this, okay. So not much. Manganese, molybdenum, sulfur, chromium, nickel. Okay, now these are just repeated anyway. And you have silicon here, yeah? So make sure you write that down. Here too, boron, see? That's a special element, yeah? So this table shows some typical applications of alloy steels. So where do we use them? Here, yeah? So if you look at it here, manganese steels, this is your composition, and this is where we use. Bicycle frames, high strength bolts, chromium, composition, and where we use. The steering parts, right, spring, steel, chromium, molybdenum, steel, composition. We use in pressure vessels, aircraft structural parts, auto axle, steering knuckles, chromium, vanadium, steels, composition, your valves, and then your springs, nickel, chromium, molybdenum, steels, composition is here, and we use in auto springs, small machine axles and shafts, your crankshafts, your silicon steel, composition, and we use in springs, okay? your leaf springs. Okay. High alloy steel. So there are two categories in high alloy. Looks like really shiny like this, so stainless steel, and tool steel. Okay, tool steel like your knife, your hunting knife. You know, you have to pay a lot of money to get a real good cutting knife. Yeah, not a blunt kitchen knife. Very different. Okay, so stainless steel. We're gonna go all the way back to our PCS, which is your plain carbon steel. We put in like about 18% chromium and 8% nickel as alloying elements. So that steel has a very high, right, corrosion resistance. We also have a ferritic and the martensite and austenite, okay, stainless steel. So here they're just showing you ferrous structures like that and the martensite structures like that. You want to know the difference, okay? There's a very microstructure anyway that you can see the difference, but then outside they have differences, okay? Steel, stainless steel. Here is the austenite, right? Ferritic, so a little bit different. And again, we can't judge by looking at it, okay? We usually judge by coding. The code is printed on it, okay? In each part. So tool steel, we call it tool steel because you can use it. They're very useful. It's a little bit better than plain carbon steel. Why? Because we put more chromium, and we also put tungsten, vanadium, other alloys. So refer to the previous table. Super alloys, okay? Super alloys are better than PCS because we have like now 50% of the alloy elements. Now we're going to use them for special purposes, okay, like a very high temperature application, like in a sophisticated national lab, NASA lab, okay? So things like that we use on silver alloy, and ISD also use them. Ferrous stainless steel is your plain carbon steel. So here you don't have to know everything. I just want you to read, okay, a little bit. So this is showing you again your chemical composition. That's just a code. And here is the application of this PCS. Okay, I don't want to read everything here again. Chemical composition, what are we putting into it? If that is the AISI 405, we're putting this, this, and that. Okay, application, you can use this. Okay, 409, you're going to use this, and you have to follow this code. Okay, you've got that, and you don't want to use this. You've got 430, and you don't want to use application of a 436. Okay, it's going to mess everything up. So the standards, alright, are very, very important. Codes are very, very important because they're standards that we strictly follow. Okay, if somebody messes up, it causes lives. Okay, loss of lives and loss of money. Yeah. So make sure you follow all the standards that you need to if you get into this type of job. Okay, Martensite is a stainless steel, right? It belongs to the PCS 1 type. And again, the same thing. Looking at the chemical composition, we have a different code, and you apply, right? Application according to the code because the composition really, really matters. Yeah. The last one, oh, not the, this is second last. So Austenite stainless steel is your PCS. The same thing, chemical composition, go according to the code, and then do the applications. Okay, and you can't mix match. You can't use the code 301 and then do the application of the 304 at all. Okay. In the last slide, the same thing. Here is for our tool steel, right? Better than our PCS. So when you look at it, the compositions are different, and we have a different code as well. And this is how we heat treat, okay? Quenching media is what we use for water, oil, and air. And application, we're going to use these things, right? You can use the M1 for D1 application or all, okay? We will strictly follow the composition and then the application, yeah? the code is that you will go and sort out your material. The material coding is so important. Okay. Alright, that's it for part 1. So for this week, I'm just going to do the recordings for your lecture, because we've got like only 2 hours to cover 8 hours lecture. So since we are in hybrid class, let's do chapter 5 and 6 lecture at home. Okay, but you can come to class. Those of you who pledge to do the hands-on activity for final project, please show up, because I'm going to give you the handout to what to do, okay, with your project. And the rest of you, you will take the regular theoretical exam, okay? Alright, I'm going to stop right here, part 1.